Okay, this is day 3 of section 5.3. 5.3, we're continuing with solving algebraic equations, trigonometric equations rather, that are algebraically intensive, require relatively intensive use of identities in order to get the job done. All right, specific to what we're going to be doing today is what happens if we end up getting potential solutions that we cannot extract from a unit circle. How do we handle it? All right, so for the first example, our instructions are we're solving 0 to 2 pi, which has been our instruction so far for, now this is day 3, and this is our first equation. 3 sine squared x minus 5 sine of x plus 2 is equal to 0. All right, the visual clues. If you have the same trig function, meaning both signs, 2 different powers, to the first to the second power, that is your clue that you need to solve it by factoring. This is the more challenging type of trinomial factoring, where your lead coefficient is something other than 1. Okay, whatever it is that you do to factor that type of equation is what you do. That has the same algebraic structure as 3a squared minus 5a plus 2. If you use guess and check, use guess and check. If you do the slide and divide thing, do the slide and divide thing. If you do that thing where you multiply the first and last terms, if you do the x, however it is you learn to get this job done, that needs to factor into this. Okay, now that we have it completely factored equal to 0, set that equal to 0, set that equal to 0. I'm going to concentrate on the right side first because that's a little bit cleaner. Sine of x minus 1 is equal to 0. Bring over that 1. The sine of what angle is 1 in the 0 to 2 pi interval. That only occurs in one spot at pi over 2. Okay, now on to the left-hand side. Take that, set it equal to 0. That 2 needs to come over. That gets us to here. Divide both sides by 3. That gets us to here. The sine of what angle is 2/3? Well, if you check your unit circle and look at the y-coordinate going all the way around, 2/3 does not appear. So there are 2 possibilities of what could be going on here. This little branch here is not producing any solutions, or we're going to get solutions, they just don't appear on a unit circle. If it's a sine or cosine, and this thing is between -1 and +1, it has solutions. We're just not able to get them from the unit circle. So, other than going to a decimal approximation, which we're not going to be doing, this is how we express our final answer. We're going to write one solution as the arc sine of 2/3. Now, we know from several days and then prior units of solving this type of equation, typically we're expecting 2 solutions. So arc sine of 2/3 is one of them. Well, if you're using the arc sine notation or arc anything notation, and that's a positive number, that's indicating a first quadrant solution. So this is some angle that exists in the first quadrant. Now, we know that sine is also positive in the second quadrant. So we'll do a degree example just to build up how we're going to get this other answer. Say that this was 20 degrees. We know that this solution has to have a 20-degree reference angle. So that means it would have to be 160 degrees. So in other words, we would take the 180, subtract the 20, and get us 160. Okay, adjusting that thinking to this particular problem. We're in radians, we're not in degrees. So instead of 180 minus, it's pi minus. Instead of a nice clean number like 20 degrees, it's the arc sine of 2/3 in radians. So these 2 guys are solutions to this equation. They're just solutions that aren't nice and clean coming from the unit circle like pi over 2. All right, one of the things that we've been discussing over the past couple days has been the idea that some equations have high risk of extraneous solutions and some do not. If it's an equation where it's just sines and cosines, or just sines, just cosines, just some pure equation, there's a very low risk of extraneous solutions as long as we're not squaring both sides. So we're not squaring both sides. It's a pure sign equation. There is very low risk of extraneous solution, which is good because the only real way you can check these guys is with a calculator. And we're assuming we're doing this without a calculator. There is no reasonable way to plug this in and check your answer like you can plugging in the pi over 2 on the right. So for quiz and test purposes, if it's this type of problem where it's going to be something where you're going to be writing your final answers in an arc type of notation, I'm not going to be giving you any possible high risk of extraneous solutions. You can assume that whatever the solution appears to be, it is. Now, it's still possible we made a mistake. Maybe there was an error getting here. It doesn't guarantee that this is correct, but there are no extraneous solutions. Okay, second example, same type of problem here. We want to solve the 0 to 2 pi interval. Our equation, 6 cosine squared minus 5 cosine plus 1 is equal to 0. The thought process for your strategy in order to solve this. We have an equation where it's cosine squared, or a trig function to 2 different powers in the equation. That's your indicator you probably want to factor. This is the more challenging type of factoring, where it's trinomial with lead coefficient something other than 1. Whatever it is you do to factor that type of problem is what you do here. Take that, set it equal to 0. Take that, set it equal to 0. For this one here, bring over the 1, divide by the 2, the cosine of what angle is a half, nice and clean, extract those solutions right from the unit circle. 3 cosine of x minus 1, bring over the 1, divide by the 3, gets us to here. The cosine of what angle is 1/3? You check the unit circle, there is nowhere on a unit circle where the x coordinate is 1/3. For a sine or cosine, as long as that's between -1 and +1, it has solutions. We're just not getting them from the unit circle. So the way we're going to express this is we're going to write the first one as x is equal to the arc cosine of 1/3. If you are using arc trig notation, whether it's sine, cosine, or tangent, and that number is positive, that's always referring to a first quadrant solution. All right, so let's do the same thing we did with the previous problem in terms of thinking our way through the process. Let's just assume for a moment that it's a nice clean answer like 20 degrees. What would the other solution be? Well, cosine is also positive in the fourth quadrant. It has to have the same reference angle of 20 degrees. So rotating in the 0 to 360 direction, it would be 340 degrees. Or in other words, 360 minus 20. Okay, translating that into this type of problem. Because we're in radians, it's 2 pi minus instead of 360 minus. Instead of a nice clean angle like 20 degrees, it's a messy angle in radians like arc cosine of 1/3. All right, third and final example for today. We're still solving the 0 to 2 pi interval. Our equation, 5 tangent squared minus 4 tangent is equal to 0. We have tangents and tangent squares mixed in the same equation. That is our indicator that we probably want to try to solve this by factoring. The factoring that applies here is to take out the GCF of tangent. That leaves this in parentheses. Set that equal to 0, solve what's there. Set that equal to 0, solve what's there. Okay, the tangent of what angle is 0? Those can be extracted right from the unit circle. Your two solutions are 0 and pi. To solve this, that minus 4 has to come over, divide by the 5. Okay, there is no place on a unit circle that if you take the y coordinate and divide it by the x coordinate, or the sine divided by the cosine, are you going to get a fraction of 4/5? So the best we can do, without going to a decimal approximation, which we're not going to be doing for this, is to write that answer as the arctan of 4/5. Okay, if you're using arc trig function, whether it's sine, cosine, or tangent, if that's a positive number, we know that's referring to a first quadrant angle. Well, we know tangent is also positive down here in the third quadrant. So let's use the same reasoning we did for the previous two problems. Let's pretend for a moment that was a nice clean answer, like 20 degrees. This solution here would have to be 200, or in other words, 180 plus 20. Well, instead of 180 plus, it's pi plus, because we're in radians as opposed to degrees. Instead of a nice clean angle like 20 degrees, it's the arctan of 4/5. So pi plus the arctan of 4/5. Okay, similar to what I had said, I think in the first example, these problems already have enough going on. We're not going to be concerning ourselves with any possibility of this type of problem where we have a high risk of extraneous solutions. You can assume if you're using this strategy that the solutions you get are actual solutions. You don't have to check them. The 0 and pi are very easily checkable, but there's no reasonable way without using a calculator to check these two guys. So we're not going to have to worry about it for this particular type of equation. All right, the other thing here, a connecting feature of these three problems was when we introduced that arc notation, this was positive, which made it a first quadrant answer. When we introduced the arc notation, this was positive, made it a first quadrant answer. Introduced arc notation, that was positive, made it a first quadrant answer. Okay, for quiz and test purposes, that's always going to be the case. We're not going to do a quiz or test question where that's going to be negative. It might pop up on homework problems or places other than a quiz or test, but for a quiz and test, time is already going to be tricky enough where the negatives and going through the line of thinking like we did is not going to be something you have to worry about. It might be on a homework, in which case deal with it and figure it out, but it's for the purposes of studying for quizzes and tests, you don't have to worry about that. That will not be an option that you're going to need to concern yourselves with.